Hello everyone, let's look at jump game. The problem statement is, we are given an array of positive integers. We are initially positioned at the first index of the array. Each element in the array represents the maximum jump we can take at that position. We need to determine if we are able to reach the last index. Let's look at the example. This is input 23114. Initially we are here at 2. And then we can jump either one step or 2 steps. So if we jump one step, we reach 3. And 3, we can jump 3 steps to 4, or we can jump 1 or 2. So if we jump 3 steps to 4, then we reach the end. That's the explanation. Jump 1 step from index 0 to 1, and then 3 steps to the last index. I guess a really straightforward solution is to try every single jump pattern starting from the 0 index. And then we only need to check if any path will lead us to the last index. This is like traverse a tree, and we need to use recursive backtracing. But if we think about recursion, it might not be the optimal solution. This is like if we want to solve a Fibonacci sequence, we'd rather use a recursion rather than using a simple loop. However, for this question, I will still explain the recursive solution. But in general, it should be categorized into dynamic programming. It's a top-down dynamic programming solution. Let's use an example here. Think about our input arrays 3, 1, 0, 2, 4. So initially, we are at position 0. That's 3. That means we can jump 1 step, 2 steps, 3 steps. If we jump 1 step, it's 1. The value is 1. We can only jump once. Then we jump to 0. 0, we won't go anywhere. So this path 3, 1, 0 doesn't work. Let's back to 3. If we jump twice, then we jump to 0. We jump to here. And then we still don't go anywhere. So 3, 0, this path doesn't work. If we jump 3 steps, then we jump to 2. And 2, the value 2, we can jump either once or twice. If we jump once, and then we reach 4. That's the last index. So we have this one path, 3, 2, 4. Reach the last index 4. As a result, we can return true. So we can easily build this tree structure and then determine if we can reach the last index. Let's look at this tree again. Well, please think of this as a tree. When we jump, we can mark a certain index as good or bad. For example, this one, index is 2. It's certainly a bad index. Because the value is 0, it won't lead us to anywhere. We end up stuck in here. Also, for index 1, the value is 1, and the next one is also 0. So this index is also bad. To sum up, we want to mark every index either good or bad, from top to down. Let's go through an example. So initially, the value is all unknown. This is unknown, 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 unknown. Okay, from top to bottom, for 3, we don't know. For 1, we don't know. For 0, index is 2. This one becomes bad. Because index 2 is bad, index 1 is also bad. So this becomes from unknown to bad. And then 2, we don't know. But next one, that's 4. 4 is good. So that's 2 is also good. And 3 is also good because they are on the same path. And all these good and bad can be saved into a memoization array. Let's call it memo. So initial value will be all unknown, and then from top to bottom, we update the value. In the end, as long as the first element for this array is good, then we know we can jump until the end based on the rule we just described here. I know you are thinking about why not we check the index in a reverse order, first from 4, then to 2, then to 0. I'm telling you, this is a really good thought. This will be the second solution. We call it a bottom-up dynamic programming. Let's first look at the implementation for the recursive top-down approach. So, first we get the length of the input array, and then we initiate our memoization array. The initial values are all unknown. And we want to update that last element. The last element should be good. And then, this is our recursive method. We pass index in as a parameter. And then, we only need to return jump 0. Let's look at the implementation for this recursive method. If the current index, the value is good, we return true. If the value is bad, we return false. And then we have this nums I. This is the value, is how many steps we can jump. For the loop, we need to have a boundary check. We need to have the mean value for the length -1 and the steps we can jump. This is because we need to have this boundary check. And then let's start our for loop. What should be the start index for this I? I think it should be index +1. If we think the starting index is index +1, then this max jump, here we should also have idx plus nums I. And then, let's do the jump again. We pass it in. We check the jump result. If it's true, then we can update the index for this memo. That's good. And also return true. Otherwise, after the for loop, if we don't add any good, it should be marked as bad and return false. And this is the recursive method. And here it should be idx, not I. So this is the how many steps we can jump, and we add this index. That's why we have I equals index +1. Let's submit. It passed, but it's takes really long time. Let's first look at the complexity here. For space, it's O of n. This is the size of our memo table. And then for time, it's O of n squared, because we have this recursive method. Obviously, we all know this is definitely not the optimal solution. Let's look at the bottom-up solution. For the bottom-up approach, let's see this example again. So this is our memo. The initial value will be bad, 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 bad. Initial value is all bad, except the last digit. The last one is good. And then, we from back to front. If 4 is good, and the next one, second last, 2 is too good. I think it is good because it can jump either 1 step or 2 steps. So we update this to good. And then we keep moving back. 0, is this good or bad? No, it's bad. We keep it like this. And then 1, is 1 good or bad? I guess it's bad. And then 3, is 3 good or bad? It's good. By doing this, we get this final memo array, and then we return the first element for this memo. Sorry, not return the first element, but to check if the first element is good. Let's look at the implementation. First, we can completely get rid of this recursive method. In the end, what we need to return? We only need to return this. As long as the first element for the memoization array is good, then we should return true. Let's look at the loop inside. We do the loop from back to front. So the start index is the second last, and then we keep -1. Inside the loop, we also have this boundary check. And then, inside this, we have another for loop. So, for the j, as long as the j is at the good position. So if j is good, then we can say I is also good. We can break this inner loop. And then we go to the outer loop. We have this is typo. We have this max jump, and then we do the inner loop again. After the for loop ends, we return this if the first element for the memo array is good. Let's submit. It passed, and this time the performance is much better than the first approach. Let's look at the complexity here. This time, space is O of n. That's the size of our memoization array. For time, it's O of n squared because we have this outer loop and inner loop. I do understand for both top-down and bottom-up dynamic programming solutions are not optimal and even confusing. If I have confused you, feel free to move back and look at the video one more time. Finally, let's look at greedy, which is supposed to be the best solution for this question. To illustrate my idea, let's look at this example again. Let me clean up this a bit. So, initially, we have a value called max jump. And the initial value is 4. 4 comes from length -1. Then we can loop through the array from back to front. We can skip the last index, and then let's look at the second last index. Index is 3, value is 2, and we need to compare the sum value 3 plus 2 if it's greater or equal than max jump. If it's greater, then we mark this index as good. The reason is because at this index, we can jump 2 steps. That's greater than 4. So we mark this as good. And then we update our max jump into 3. That's the index for this good index. And then we keep loop. We move to index 2. And index 2, the value is 0. So we add them together. We get 2. 2 is less than max jump. So we mark this as a bad index. And we don't update our max jump. Max jump is still 3. And then we move to index 1. Value is also 1. We have 1 plus 1, that's 2. That's less than max jump. Still, we mark this index as a bad index. And we don't update our max jump. And then we move to index 0. Adding them together, 0 plus 3 is 3. So we mark this as a good index. And then we update our max jump to be 0. After the loop, if the max jump value is 0, then we can return true. If I have confused you, let's look at the implementation. I can confirm it will be clear when we look at the code logic. This is our max jump initial value, and then let's do the for loop. Same thing here, we start from the second last. If the sum value is greater or equal than max jump, then we update max jump. After the for loop, we return if max jump equals 0. Let's submit. It looks good. Let's look at the complexity here. For space, it's constant. For time, it's O of n. We have this loop here. I'm sorry this video is a bit long. I hope you find this explanation useful when you look at this question. Thank you for watching. If you have any question, please leave a comment below.